In this video, I'll be walking through my notes on NCEA Level 3 Modern Physics. A link to the PDF and a list of corrections is in the video description. Photoelectric effect. When photons of sufficient energy strike a metal surface, electrons are ejected. Here we have our metal surface, our incident photons, and our ejected electrons, or photoelectrons. The energy required to eject electrons from a metal is called the work function of the metal. Here we have a collection of metals and their respective work functions. The unit for energy we're using is electron volts, which we'll be covering in the next section. The photoelectric effect demonstrated particle-like behavior of light at a time when a purely wave theory of light was widely considered sufficient. Assuming light was a wave, the favoured explanation was that light shining on the surface slowly heats up the particles, causing them to emit electrons. We're now going to go through some expectations based on the wave theory of light and the observations which showed particle-like behaviour. Based on the wave theory of light, we would expect that increasing brightness would increase metal temperature and increase the kinetic energy of the electrons. In reality, more electrons were ejected and the kinetic energy was unchanged. Based on the wave theory, we would expect that dim light would take longer to heat the surface and eject electrons. In reality, using UV light, electrons were ejected immediately. Based on the wave theory, light frequency would not affect electron energy, when in reality, increasing light frequency increased electron kinetic energy, and there was no ejection below a threshold frequency. I have here an electroscope, a device used to indicate the presence of charge, atop which is a plate of zinc metal. Adding electrons to the metal with a balloon, imparting a negative charge, we can use ultraviolet light to eject the electrons from the metal, removing the negative charge. This is called the photoelectric effect. Repeating this process but with a sheet of glass in between, glass blocks the high energy ultraviolet, the remaining lower energy photons lack the energy to overcome the work function of the metal. Lastly, we can remove electrons by bringing the negative balloon close and providing a pathway for the electrons to escape. The metal is now positively charged. The ultraviolet light fails to remove the positive charge because the photoelectric effect can only remove electrons, which will only increase the positive charge. I have here a photoelectric smoke alarm, taking it apart to get a better look at how it works, and adding a lump of plasticine to quieten the speaker. An infrared LED illuminates a ventilated chamber, with a photodiode positioned on the other side, such that under normal conditions, the infrared light is reflected away from it. However, if smoke were to enter the chamber and scatter the infrared light, a portion would now reach the photodiode. A photodiode detects light using a variation of the photoelectric effect called the photovoltaic effect. Within the photodiode is a semiconductor, and within that is a non-conductive region called the depletion region. When a voltage is applied to this region, while the photodiode is dark, current does not flow. However, if photons of sufficient energy strike this region, the electrons are excited into higher energy states, in which they're now free to move. Applying a voltage will now produce an electric current, which is used to trigger the alarm. Electron volts. When describing energies on a particle scale, it's useful to have a unit of energy appropriate to the scale. For this, we define an electron volt as the energy required to move an electron through a potential difference of 1 volt. Electric energy is given by QV, where our charge Q is just our electron charge E, which is 1.6 times 10 to the negative 19 coulombs. Multiplying that by our 1 volt, we get that an electron volt is equal to 1.60 times 10 to the negative 19 joules. To convert electron volts to joules, we multiply by this number. To convert joules to electron volts, we divide. Photoelectric cells. Photoelectric cells produce electrical current via the photoelectric effect. The cells consist of an emitter, upon which an incident light ejects electrons, which are collected by the collector. A voltage can be applied to determine the kinetic energy of the electrons. The stopping voltage is achieved when the kinetic energy is fully consumed into electric potential energy and current ceases to flow. This kinetic energy, equal to our electric potential energy, is equal to our electron charge multiplied by our stopping voltage. Photons. Whereas phenomena such as diffraction demonstrates light as behaving like a wave, phenomena such as the photoelectric effect demonstrate particle behavior. The compromise is to consider light as a quantized wave packet, which we call a photon. The higher the frequency, the higher the energy. The exact relationship is that the energy is Planck's constant multiplied by the frequency. Let's now go through an example. Calculate the energy of a photon with a wavelength of 565 nanometers. Our wavelength of 565 nanometers is 565 times 10 to the minus 9, because nano is times 10 to the minus 9. To find our energy, we need to use the equation E equals hf, where we don't know the frequency, but we know the wavelength, and we know the wave velocity. Because it's a photon, it is the speed of light, 3 times 10 to the 8. So we can use V equals f lambda, solving that for frequency, by dividing both sides by lambda, putting our numbers in, gives me 5.31 times 10 to the 14 hertz. And now putting that into our energy equation, gives me 3.52 times 10 to the minus 19 joules. Photoelectric equation. The photon energy is consumed to liberate the photoelectron from the metal, which is our work function phi, and any excess energy adds to the photoelectron's kinetic energy, Ek. Put mathematically, our photon energy goes into liberating our photoelectron, and anything left over is our kinetic energy. If the photon energy is less than the work function, then no electrons will eject. The photon energy will instead be used to heat the metal. And so we see we have our work function here. Our photon energy is not quite enough to fulfill this. If the photon energy is equal to the work function, the electrons will eject but with no kinetic energy. If the photon energy is more than the work function, the electrons will eject and they will have kinetic energy. So our photon energy is used to liberate our photoelectron, and then we have left over for kinetic energy. Let's now go through an example. A photon of frequency 12.5 times 10 to the 14 Hz strikes an aluminium plate with a work function of 4.26 electron volts. Calculate the maximum kinetic energy of the ejected photoelectron. We know our frequency, and we know our work function is 4.26 electron volts, which we can multiply by the charge of the electron, to give us 6.82 times 10 to the minus 19 joules. And now using our equation that our photon energy is equal to our work function plus our kinetic energy, solving that for kinetic energy, we just put our numbers in, which gives us 1.47 times 10 to the minus 19 joules. Photoelectric threshold frequency. The work function gives the energy required to liberate photoelectrons. Since photon energy is related to its frequency, we can also define a minimum frequency. Since E equals hf, at E equals the work function, we can write that the work function is hf, where our f is the threshold frequency. The threshold frequency is most often in the ultraviolet spectrum. Here are the same metals from earlier, and here are their threshold frequencies. Photoelectric stopping voltage. Consider the following circuit with a photoelectric cell, a voltage source, and an ammeter. When the voltage is such that the electric potential energy gained by the photoelectron equals its kinetic energy, current ceases to flow, and so our electric potential energy equals our kinetic energy, and since EP equals QV, and our Q is our charge of our electron E, EP equals EV. Since our photon energy is equal to our work function plus our kinetic energy, we can rearrange this for EK. Knowing that these two are equal, we can replace EK with EV.
Let's now go through an example. A photon of frequency 2.71 times 10 to the 14 Hz strikes the emitter plate in a photoelectric cell with a work function of 0.650 electron volts. Calculate the stopping voltage. We know the frequency, and we know our work function. To convert that to joules, we just multiply that by the charge of the electron, which gives us 1.04 times 10 to the minus 19 joules. At the stopping voltage, we know that the electric potential energy, which is equal to EV, is equal to the kinetic energy of the photoelectron, which is the photon energy minus the work function. We know this equation here because we know that voltage is energy per charge, where our charge is the charge of the electron. Rearranging that for energy gives us EV, which is our energy here. And we know this equation here from our equation that the photon energy is equal to the work function plus the kinetic energy. Solving that for our kinetic energy, EK, gives us HF minus phi, which is this here. We can now solve this equation for our voltage by dividing both sides by the charge of the electron. Putting our numbers in gives me 0.473 volts.
Photoelectric graphs. Graphing the intensity of light versus the current in the circuit, we observe an increasing trend because a higher intensity means more photons, which means more photoelectrons, which means more current. Plotting our frequency versus our maximum kinetic energy, we see that below a cutoff frequency, our kinetic energy is negative, meaning there is no emission. In order to eject electrons, the minimum energy we must provide is the work function of the metal. Above this cutoff frequency, our slope is h, as E is equal to hf, where this is our y, this is our x, and this is our gradient m. Plotting a graph of current and voltage, we see that below a certain cutoff voltage, we get no current, as the voltage is sufficient to repel all of the photoelectrons. Above this, we see an increasing current, and at zero voltage we have zero potential. At a certain point our current stops increasing and we reach a point of saturation. For high intensity light we have more electrons being ejected, so we reach a higher current. The Bohr model. Several years later the Bohr model was developed to align with mounting evidence of quantized electron energies within the atom. It consists of small negatively charged electrons orbiting at distinct distances, and positively charged protons and neutrally charged neutrons existing in a dense central region called the nucleus. Hydrogen energy levels. The energy of an electron in the nth shell of a hydrogen atom is given by En is equal to negative Planck's constant multiplied by the speed of light multiplied by Rydberg's constant and divided by the energy level squared. The negative sign indicates that electrons bound to an atom have a deficit or debt of energy. Energy must be repaid in order to liberate an electron from an atom. Furthermore, the lower the shell number, the higher the debt. Excitation energy is the energy required to excite an electron to a higher shell, whereas ionization energy is the energy required to liberate an electron from an atom entirely. Hydrogen energy levels appear in distinct groups due to energy differences between series being much greater than within. The Lyman series gives transitions to the first shell, Balmer to the second, Paschen to the third, Brackett to the fourth, and Pfund to the fifth. Let's now go through an example. An electron in the fifth energy level of a hydrogen atom transitions down to the second. Calculate the energy of the photon released. We know our equation for the energy of an electron in the nth level, so we can find the energy of the electron in the fifth level by putting in our speed of light, our Planck's constant and our Rydberg constant, and for our n we have 5. That gives us negative 8.75 times 10 to the minus 20 joules. To find the energy in our second energy level, we do the same thing, but now with an n value of 2, which gives us a negative 5.47 times 10 to the minus 19 joules. To find the energy of the photon, we need to find the difference between these energy levels. Putting those numbers in gives us negative 4.59 times 10 to the minus 19 joules. Atomic line spectra. When electrons within a gas are excited, they transition to higher energy shells. As they transition back down, they release the energy difference as light. So we have our atom, we excite our electrons to higher shells, and they drop back down and emit light. Conversely, electrons will transition to higher energy shells by absorbing light with the energy required for an available transition. So we can have the opposite process, where instead of electrons transitioning down and emitting light, we can have electrons absorbing light and transitioning up. Since the transition energies are different for every element has a unique fingerprint of colors that they absorb and emit. We call these atomic line spectra. Here are a few samples, where on this end we have long wavelength, low frequency and low energy, and on the other end we have the opposite. In this experiment, I'll be passing high voltage electricity through glass vials of gas. As the electricity passes through the gas, the electrons are excited into higher shells, and as they transition back down, they will emit distinct wavelengths of light. By placing a diffraction grating in front of my camera, we're able to separate this light by frequency and see clearly our spectral lines.
I have here a Bunsen burner, metal gauze to dip in a solution of sodium chloride, a normal LED lamp, and a high pressure sodium lamp. Turning on the normal LED lamp and heating the soaked gauze, we see nothing peculiar. Repeating this with the sodium lamp, we see the flame cast a shadow. This happens because gases, in this case sodium, have a specific selection of colours which they emit and absorb, which we call atomic line spectra. We can view these colours separately by placing a diffraction grating over the camera and narrowing the light to a strip. The colours produced are from the sodium in the lamp. These are absorbed by the sodium vapour, causing it to cast a shadow. These other colours are from the mercury also present in the lamp and are not absorbed by the sodium vapour. The normal LED lamp does not cause a shadow because it produces a continuous spectrum of light, of which the colours absorbed by the sodium vapour are only a small selection.
Hydrogen spectrum. We can use Rydberg's formula to describe the spectral lines for hydrogen, where 1 over our wavelength is equal to Rydberg's constant multiplied by 1 over our lower shell squared minus 1 over our higher shell squared. For example, an electron transitions from the 4th shell to the 1st. We start with our equation, solve it for lambda, substitute in our numbers, and get 9.72 times 10 to the minus 8 meters for our wavelength. This is an aurora. It occurs when charged particles from the Sun enter Earth's atmosphere and excite the electrons within its gaseous particles. The composition of our atmosphere is mainly nitrogen and oxygen, therefore the wavelengths of light we see are primarily from these two atomic line spectra. Periodic table basics. The periodic table displays elements in order of size and electron configuration. From our element symbol, we have our atomic number, which is the number of protons, and if the atom is electrically neutral, it is also the number of electrons. And our atomic mass is the combined amount of protons and neutrons. You may ask, why is this a decimal? This is because periodic tables typically give the atomic mass as an average across all the isotopes, weighted by their abundance. And now to make things simple, here's a table of how to find the amount of any given particle. The proton is always the atomic number, the electron is the atomic number if the atom is electrically neutral, and the neutron is the atomic mass minus the atomic number. Isotopes. While every element has a fixed unique amount of protons, its amount of neutrons can vary. We call these different versions isotopes. For example, there are 3 main isotopes of hydrogen. Hydrogen 1 with an atomic mass of 1, hydrogen 2 where we add a neutron, giving us an atomic mass of 2, and hydrogen 3, which adds a further neutron to give us an atomic mass of 3.
The strong nuclear force. Nucleons, which are protons and neutrons, the things that reside in the nucleus, are made from smaller particles called quarks. For example, a proton is made up of 2 up quarks and 1 down quark, and the neutron is made of 2 down quarks and 1 up quark. The attractive force between quarks is called the strong nuclear force. This force also extends outside each nucleon, causing them to attract other nucleons. And so we're saying that this attraction between the quarks is so strong that it's able to also attract the quarks in the other nucleons. It acts over a relatively short distance, so has little effect between nucleons that are far apart. And so if we have our collection of nucleons, all of our nucleons will attract each other. However, because the force only acts at a short distance, this nucleon here is only going to feel a significant force from these nucleons here, and not any of these nucleons here. This becomes important when we consider the other force acting. The Coulomb force. The Coulomb force acts to attract opposite charges and repel like charges. Because protons are positively charged, a repulsive force exists between them in the nucleus. Because neutrons are uncharged, they do not experience this force. The Coulomb force is weaker than the strong nuclear force, but it acts over a much larger distance. And so once again, considering all of our nucleons, if we were to look at this proton here, it's going to experience forces from all of these other protons, since it acts over a much larger range. Nuclei stability. While the strong nuclear force holds a nucleus together, the Coulomb repulsive force acts to push it apart. The stability of a nucleus depends on the balance of these forces. For small nuclei, the strong nuclear force easily overcomes the Coulomb repulsion. For larger nuclei, the Coulomb repulsion is significant enough to reduce the stability of the nucleus overall. And so if we were to graph the nuclei size against the stability, we see that the stability increases initially, as more nucleons means more strong nuclear force. However, the stability decreases as the Coulomb repulsion becomes more significant over large separations.
Alpha, beta, and gamma radiation. In this course, we will be considering 3 types of radiation. Alpha radiation consists of 2 protons and 2 neutrons, which is essentially a helium nucleus. It's emitted when a nucleus is too large to be stable. It is the largest and slowest of the 3 we'll talk about, and because of its 2 protons, it is positively charged. Beta radiation is an electron, which is emitted when a neutron decays. They travel near the speed of light, and since it's an electron, it's negatively charged. Gamma radiation is an electromagnetic wave. It's emitted when a nucleus has excess energy, travels at the speed of light, 3 times 10 to the 8 meters per second, and has no charge. Energy and mass. Energy has mass, and mass has energy. This is known as mass-energy equivalence. Described by the famous equation, energy is equal to the mass multiplied by the speed of light squared. This means that 1 kilogram of mass is equivalent to a very large amount of energy, roughly the amount of energy released by the nuclear bomb dropped on Nagasaki in 1945. For a continuous nuclear reaction, we can write the power output as power is energy over time.
Mass from kinetic energy. The mass of an unmoving object is called its rest mass. However, as an object moves, it gains kinetic energy, so it must also gain mass. And so if we have an object at rest, its total mass is just its rest mass. However, if this object is now moving, the total mass is now this rest mass plus its moving mass. Let's look at an example. The rest mass of a neutron is 1.67 times 10 to the minus 27 kilograms. If a neutron is released from a nucleus at 1.98 times 10 to the 7 meters per second, it will have a kinetic energy of Ek equals half mv squared. Putting in our mass and putting in our velocity gives us 3.27 times 10 to the minus 13 joules. Since we know that E is equal to mc squared, we can rearrange this for the mass, giving us E over c squared, and so this kinetic energy corresponds to an increased mass, which we can write as kinetic energy over c squared. Putting in those numbers gives me 3.63 times 10 to the minus 30 kilograms, which is negligible compared with the rest mass. What I mean is that although this number is pretty small, this number is much smaller, by a factor of roughly 1,000. Nuclear binding energy. When nucleons are bound in a nucleus, they have less energy than when they are free. This difference in energy is called the nuclear binding energy. The corresponding mass difference is called the mass deficit. When nuclei move from a less bound state to a more bound state, they release energy. For nuclei smaller than iron, this is achieved by fusion. For nuclei heavier, this is achieved by fission. We can see this better by looking at this graph, which shows the amount of nucleons in a nucleus against the binding energy per nucleon. And so the bottom of our graph shows less bound, and the top of our graph is more bound. And so in order to release energy, we must move from a less bound state to a more bound, which means we must be moving upwards. By graphing the binding energy of our nuclei, we see that there are two ways to do this. We could ride the curve upwards here, which would be making smaller nuclei into larger nuclei, or in other words, nuclear fusion. Or we could ride the curve upwards this way, which is splitting larger nuclei into smaller, or in other words, nuclear fission. At the top of our mountain is the atom iron, which is the most bound of all the atoms, and whether you try to fuse or fission it, it will not release energy. Finding the binding energy of a nucleus. Let's determine the binding energy of iron. For this we need to know the mass of iron, the mass of a proton, and the mass of a neutron. Iron has an atomic number of 26 and an atomic mass of 56. An iron nucleus therefore has 26 protons and 30 neutrons, 56 minus 26. The bound mass is our mass of iron, 9.2882 times 10 to the minus 26. The unbound mass is the sum of the individual unbound proton and neutron masses. And so we take the total mass of our protons, which is 26 protons times the mass of each proton, and the total mass of our neutrons, which is 30 times the mass of the neutron. Important to note, these are the unbound masses. If we were to instead measure the proton and neutron mass inside of a bound atom, that value would be smaller. Putting those numbers in gives us 9.373 times 10 to the minus 26 kilograms. The difference between these masses, which we call the mass deficit, is our bound mass minus our unbound mass, which gives us 8.48 times 10 to the minus 28 kilograms. The corresponding energy is the binding energy, which we can find using E equals mc squared. Putting our numbers in gives me 7.632 times 10 to the minus 11 joules. And so this amount of energy is the total amount of energy our protons and our neutrons would lose as they come together to bind into an iron atom. And going the other way, it's the amount of energy we'd need to expend in order to separate an iron atom into its constituent protons and neutrons.
Conservation laws. When a nuclear reaction occurs, the following quantities are conserved: mass number, atomic number or charge, momentum, and mass energy. Note that mass and energy separately are not conserved. However, mass energy is, which is a quantity that recognizes E equals mc squared. Nuclear fission. Nuclear fission involves the splitting of a nucleus into smaller nuclei. There are two types of nuclear fission: spontaneous, which occurs without intervention, where an unstable parent nuclei spontaneously decays into its daughter products. Induced is initiated by an incident particle. So if we have a stable nucleus and fire a particle at it, the resulting nucleus splits into our daughter products similar to before. Once again, the difference is the incident particle. A chain reaction occurs when particles released in one reaction are able to induce subsequent reactions. Nuclear reactors use chain reactions to achieve self-sustained energy production. Unlike reactors which are designed to achieve a steady rate of reaction, nuclear weapons are designed for uncontrolled, high-yield runaway reactions. Here we have a useful analogy for a chain reaction. We start with one reaction, which has the potential to trigger more reactions, and those reactions more of their own. The result is a rapidly increasing rate of reaction. Nuclear fusion. Nuclear fusion involves the combining of two or more nuclei to form larger nuclei. Here is one of many examples. For nuclear fusion to occur, the nuclei must travel with enough energy to overcome the Coulomb repulsion between the protons. The very high temperatures required for this to occur, upwards of 10 million degrees Celsius, are challenging to achieve on Earth. In the year of 1958, the US Army detonated 35 warheads amongst the Marshall Islands. The test we're about to see detonated a 9 kiloton warhead at a depth of 150 meters. Five years later, a number of governments, including the US, signed a treaty that would ban many forms of nuclear testing, including the one we see here.